feel. Lay on the out and out, preach your words and verbs and academic sermons. Come along with me, take my hand and do some learning.
Welcome. Let's do some math.
In this video, we're going to talk about some slightly more advanced topological concepts, namely concepts that relate to my own research. And of course, I'll be biased, I think it's pretty cool, but hopefully you'll find it cool as well. Let's get started. We say that a knot is a continuous map, often denoted K, from the one sphere, which is simply just a circle, into the three sphere, which we'll explain more about in a second. This map, besides being continuous, should be bijective onto its own image. That is, if you just restrict the codomain to the image, it should be bijective, and have a continuous inverse when it's restricted on its codomain. Now simply, we take the one sphere, S1, we map this in some way into three-dimensional space. We call that mapping K, and the three-dimensional space is like what we're used to with the addition of a point at infinity. Just in the same way, the one sphere is just the real line with a point at infinity. As we map the one sphere into the three sphere, which is just again R3 plus a point at infinity, we can trace out a knot. This image under the map is what we call the knot itself, and sometimes the image is called K. While knots exist in three-dimensional space, and we can think of them as something that we could touch and manipulate, just as we do three-dimensional objects tied into knots, in order to work with them in a more convenient capacity, what we'll want to do is look at knot diagrams. A knot diagram is simply a projection of a knot into the plane such that the crossing information after the projection is recorded. When we do the projection, we have to make sure that there are no points of self-intersection that intersect more than twice. They're not triple points or quadruple points, they're only double points. That is, there's only, in some sense, an overlap twice. And we do have to make sure that we are able to capture the crossing information. Diagrammatically, here's what it might look like. Say we start with a knot that I've tried to draw in a three-dimensional sense, and it's floating in three-dimensional space. Then we project that knot onto a plane, but notice when we do the projection, there are these points where we're not sure which strand of the knot goes over which other strand. That's the crossing information that we need to keep track of. And in particular, we have to have that these points, we don't have more than two strands crossing. That allows us to capture the crossing information of the original knot. So we resolve each of these crossings to know which strand is above the other one. So notice here, this crossing has been resolved from this self-intersection to show that over here we have one strand over the other. And that's maintained for each of these crossings. The crossing is projected and now looks like a self-intersection. And then we record the information to show us which strand crosses over which. This, in the end, is the knot diagram. Now here's where things start to get fun. You can have a single knot represented by more than one knot diagram. For instance, we can have the unknot, which is simply the one sphere, just a circle with no obvious knotting, but we could have different diagrams that still represent this knot. For instance, we could have this diagram, where there's essentially just a twist, or we could have a diagram like this. And there could be much more complicated diagrams that still represent just the unknot, which is pretty neat. With these particular knots that we've shown, if we do an untwist here, we'll get back to the unknot. And with the right diagram, if we first pull up the strand behind and then do an untwist, we'll also get back to the unknot. However, we can have diagrams that look different and indeed represent different knots. Here's the unknot again, and then a knot that is completely distinct from it. There's no amount of isotopy we can do to this diagram to get to the unknot. So these distinct looking diagrams actually represent distinct knots. But distinct diagrams don't necessarily mean they're representing distinct knots. Now there are a lot of distinct knots. There's an infinite number of them. But But if we even restrict just to 12 crossings or fewer, there's almost 3,000 distinct knots, and they grow pretty quickly. The minimal crossing knot we can have is 0 crossings, which is the unknot, and there's just a unique one. There's no single crossing knots we can have. That is a knot with a minimal number of crossings being 1. Likewise with 2. For 3 minimal crossings, there's only 1 knot. Same with 4 minimal crossings. That increases to 2 with 5 minimal crossings. Once we get to 8, we're looking at 21, which is not too many. Jumps up quite a bit with 9, and then by the time you get to 10, we're looking at 165 distinct knots. Of course, this says up to 12 or fewer, so 11 and 12 have thousands. So there's many different knots. There's lots of knots out there, and they have a lot of interesting properties. When looking at knots, one thing to study are invariants. And there are many different types of knot invariants. A knot invariant is a number or an algebraic object assigned to a knot diagram that if you have another knot diagram and it represents the same knot, you'll get the same number or the same algebraic object. So it's invariant as in it doesn't change as long as you don't change the knot. So the diagrams can change, but the knot should not change. There are many, many invariants. Here's a list of some. This is taken off of Knot.info, a site that I rather like and is useful for getting information about knots quickly. But this is just a partial list of all the different invariants. So here are 3D numeric invariants. That is, these are each just a number assigned to a knot in different ways. There are 4D numeric invariants. There are polynomial invariants, invariants where you assign a polynomial to a knot diagram. And this is not even nearly a complete list of all the different invariants. The one that we'll study is related to the genus that you see here, 4D and topological, but what we'll look at is the CP2 genus. And notice that's not even something that was listed here, it's something that I've added, that I wrote here. So there are many invariants, we'll just look at a particular one. So let's go ahead and jump into it. Let's suppose that we start with a knot and it's tame and oriented. Briefly, tame means that it doesn't have wild behavior where it stretches off to infinity or gets infinitely smaller knotting in places. Oriented means that you can put a string direction on the knot and follow it around and always go in the same direction. If we have such a quote-unquote nice knot, we say a Seifert surface is a compact, connected, oriented surface S. It's embedded in S3, which again, think of S3 as just R3 plus a point at infinity. And the particular thing about this surface is that it has the knot as its boundary. Here's a picture I've drawn of such a thing. In this case, we have the knot, which is K, in the sort of lavender color that is along the border. And then we have the Seifert surface, which is two-sided. What that means is that we have orientable surface. Two-sided and orientable are not always synonymous, but in the case when we're taking a surface to be an S3, it will be. So that Seifert surface is two-sided, maybe a greenish side and a bluish or cyan side. Now, there are many terms that may not be familiar. We mentioned tame, oriented knot, an oriented surface, connected surface, compact. We talked about connected, and I mentioned what tamed and oriented are, but we haven't looked at compact yet. So there's a lot of different terms for us to suss out, and we won't go into detail with all of these, but we want to kind of get an idea before we proceed. So let's look at tame knots, oriented knots, compact surfaces, connected surfaces, oriented surfaces, and even then, let's talk about what an embedding is. And we'll just run through this briefly. Here's an example of an oriented knot. Notice that you can follow the arrows around the knot. If you can follow arrows around the knot, that means it's oriented. Unoriented means that if you follow the arrows, you'll at some point go against the direction of some of the arrows. Or we could have it that there just is no orientation on the knot. To be tame versus untame, tame is just something like this as a base. Untame would be something where your knotting could get smaller and smaller and smaller. You could extend the knot off to infinity. And one way to think about it is you have tame knots and then you have wild knots. To be compact means that we can simply fit it into a box with finite dimensions. To be not compact means that we have the manifold extending off to infinity or having other sort of similar strange behavior like this. If it is connected, it's essentially one piece. If it's not connected, there are two or more pieces. A surface is orientable if there are two sides like we see on the left, but if there's just one side like we see on the right, as in the case of a Mobius band, then we would consider that unoriented. Two-sidedness is not the same as oriented in general, but a surface embedded in 3-sphere means to be two-sided if it's oriented. Now, we've talked about manifolds here and given a mostly formal definition, but we haven't said what a manifold with boundary is here, which will be the primary type of manifold we look at, namely manifolds with not boundaries. Like we see here in the oriented case, this lavender boundary is the knot, or in this case, we have this golden boundary being the knot. So these are surfaces that are bounded by knots. Let's talk about what it means to be a manifold with a boundary. We say a topological space M is a n-manifold with boundary if it's the same as a n-manifold, with one exception. We can have points x in M and an open set around those points, and instead of just having a particular type of homomorphism that we've described before, now there's two different types of homeomorphisms that we can have. The first one is exactly the same type as we had before, or we can have this new type where instead of going from the open set to Rn, we go from the open set to Hn, which is just like Rn, except for one of the axes, we cut out the negative numbers. If you take all the points where there is such a map here fitting B, take all those together and we call those the boundary, denoting it with this notation here. Let's take a look at what this means diagrammatically. If we have, let's say, this torus that has been cut, and we look at points on the torus, let's say we in particular look at this point on the left. Around there, we can find this open set U in yellow and white, and then map that into R2 so that really this little circle here, or this disk, is just like R2. However, on this cut torus, if we look at a point here on this kind of edge, as it were, we can't map that into R2 because it's somewhat cut off, as it were. So what we do is we say we map that neighborhood into H2, which is just like R2, except we cut off this axis here. And we can see that the neighborhood around here looks like it's kind of cut off, just like in H2. The set of points where we have a map into H2, or Hn in general, that set of points makes up the boundary, which I've denoted in cyan here to match up with this notation. Anything that's not on the boundary is often said to be in the interior of the manifold. Now let's look at some examples of manifolds with boundary. In the first line, we have a one-dimensional manifold, and it has boundary. Its boundary is simply these two endpoints here. So these two taken together make up the boundary of this manifold M. In the second row, we have a disk with a boundary manifold. If the disk is two-dimensional, the boundary manifold will be one less dimension, so it's one-dimensional, and it's actually simply the unknot. We have another case of a disk. It's just deformed slightly, but again, the boundary is a one-dimensional thing, and it's, again, the unknot. Here we have a surface, and it now has a boundary that's a different knot. That's not the unknot, but nonetheless it's a knot. And notice again, your boundary is always one less dimension than your manifold. So if you have a two-dimensional manifold with boundary, its boundary will be one-dimensional. You have a one-dimensional manifold with boundary, its boundary will be zero-dimensional. It's always one less. If you had a three-dimensional manifold, its boundary would be two-dimensional. And as another case, here we have actually another unknot, and it's bounding a surface, and that surface happens to have only one side. This is the Mobius band. Now, one of the many things that I personally like about topology is that you can do cool things like surgery, which is essentially taking out parts of a manifold, gluing back in new parts, and getting totally different objects, or what seem like totally different objects. It's just so cool, in my opinion. I really like it. Let's take a look at what surgery is more accurately, but in order to do that, let's talk about products of manifolds. If we take the product of two manifolds, let's say a manifold M that is m-dimensional, and then a manifold N, which is n-dimensional, their product m times n is a m plus n dimensional manifold. And we should really look at examples right away to see what the heck does this mean. Say our two manifolds are S1 and R. These are two one-dimensional manifolds. If we take their product, it works like this. Take the first manifold, S1. When you cross it by R, you're simply taking a copy of R, and for every point of R, you're going to have a copy of S1. So the point at which we've matched up S1 with R here, there's one copy of S1. But then we get another copy, and another copy, and another copy, and so on. And this would happen everywhere on the real line. And if you put all these together, what you get is something like this, where this would be filled in infinitely. So you have infinitely many circles here, and they extend off to infinity because R extends off to infinity. So this infinite cylinder going infinitely upward and downward, that would be S1 cross R. In another example, say we have S1 and then another copy of S1. Likewise, when we do the product, what we do is we start with S1, then for each point of S1, we have a copy of the other S1. It looks like this. Notice for every one of the points on pink, in theory, we have a copy of this S1, which is a reverse order from what I said here. It works out the same way. So each point of R, we had a copy of S1, or we could say at each point of S1 here, we have a copy of this S1. And if you clean that up, it looks like this, which is the torus. So S1 cross S1 is what we call the torus in general, or to be a little more specific, the two torus. Now what's really cool is you can imagine higher dimensional tori. So try to imagine, if you could, what is a 3 torus? Well, that's S1 cross S1 cross S1. Now why did I write it rotated like this? Because it's crazy. Okay, moving on. An important fact that we'll use is if you take the boundary of a product, it's equal to two pieces. Those pieces are the boundary of m cross n, and then m cross the boundary of n. If you've learned any calculus, or when you do learn calculus, this is similar to the product rule. Now let's say, as an example, we take a product of two manifolds. Each of the manifolds will be simply the unit interval, and if you take the product, you're just going to get a square or rectangle, topologically the same. And now, if we want to look at the boundary of this thing, there's two pieces to it. In whole, it would be simply this white outer part, but it's made up of two pieces, a cyan piece and a magenta piece. The cyan piece, if we take the boundary of m and cross it with n, we get this. And for the magenta piece, if we take m cross the boundary of n, we get this. And of course, putting that back together, we get this, where we've just colored the particular pieces of it. Now let's see how we can use this to serger manifolds, to perform surgery on manifolds. This is just so neat. I love it. Now, of course, there's medical surgery, which is its own thing, but then there's mathematical surgery. What's perhaps different about mathematical surgery is that it always involves taking something away and then putting something back. And what you're doing is you're changing from one object to another by removing a part of a manifold and then putting in another part of the manifold. So notice, as I've colored here, we're going to remove something like this, and then we're going to glue back in something like this. And these are exactly the two components of the boundary of the product m cross n. So let's see how it works. We're going to use this fact about the boundaries. So we're going to take this manifold, which is m cross n. We're going to look at its boundary. That boundary is divided into two parts, the cyan part and the magenta part. So here's what we're going to do. We're going to take a manifold f. We're going to remove this part and then glue back in this part. The manifold f that we'll look at is S1. On S1, we'll identify the cyan part. So here we have S1, but now there's a part of it that's highlighted. This is going to be the part we remove, and then after that, we're going to glue back in this magenta part. So we're removing this part to glue back in this part. Taking S1 and then removing the cyan part, we simply get this. Just remove cyan part. Okay, that's what we get. Now, here's where it's cool. We glue back in the magenta part and we see what changes. Okay, so let's do that. We're going to take exactly this here, and then we're going to glue in this magenta part. And maybe you can see already what it's going to be. It's this. So we've taken away cyan and we've glued in magenta. So we've changed this from a single S1 to two S1s. Really, these are just two circles, which we can sort of smooth them out and it looks like so. So that's, to me, really cool, particularly because it has very interesting ramifications when you look at more complex manifolds. So here we've just turned S1 into two S1s simply by removing this part and then gluing in this part. But you can do surgery to get all sorts of other crazy cool things. Now, the next part of this is looking at what's called a cobordism. It's a way to relate the aspects of the different manifolds you got from doing surgery. So we had a manifold to start with, the S1, and then we had these two S1s at the end after doing this surgery. Connecting those two together, we can create something called a cobordism. A cobordism is simply a manifold that on its boundary have two particular manifolds. Let's look and see how this goes, and we'll get something kind of funny in the end. Now, what we just did, looking at mathematical surgery, is we took a manifold, the one sphere S1, we highlighted a teal part, which is part of the boundary of another manifold. If we thought of the manifold in yellow, that is just the interval cross the interval, or M cross N, it has the cyan component, and then it has the magenta component. What we do is we essentially nestle this thing in so that it lines up, part of its cyan boundary lines up with the manifold that we're doing surgery on, which is this S1. We remove everything except the magenta part. If we do that, we end up with this. Now, let's connect this to this, and we do it like so. Notice here we have the manifold we ended up with. Here we had the manifold we started with. And there's something in the middle called a cobordism. And what I love about this is through a simple surgery, linking them with a cobordism, we've created pair of pants. All right, okay, let's be serious. Pair of pants. Now, as we mentioned before, we were looking at knots and then surfaces bounded by these knots. For instance, here we have a knot, and here is that same knot bounding a particular Seifert surface, where remember a Seifert surface should be something that is two-sided. Now, there's an interesting question you can ask. That is, what is the genus of this surface? Any surface that has a single boundary component, and the boundary component here is the knot, any such surface that's orientable, compact, connected, can be defined by something called its genus. There's a classification of such surfaces, and it goes like this. You can start out and have a single boundary component, but have what's called no genus or genus 0. Then you can add genus to this while maintaining still one boundary component, where we think of this boundary component as the knot. But if we add one genus, we get something like this. Where again, think of this part here that is in the sort of lavender. Think of that as the knot. It's just simplified for the sake of the diagram. The genus part is exactly this donut part right here. And nothing is saying that you can't have higher genus. You could have genus 2, any finite number of these. What's interesting to ask in the case of a knot is essentially how low you can go. Using surgery, it's actually pretty easy to increase the genus of a knot, but not so easy to decrease the genus. Now let's say we have a closed 4 manifold. Closed just means it does not itself have boundary and it's compact. 4 manifold means at every point there's a open neighborhood around it such that that homeomorphically maps to R4, whatever R4 looks like. We'd say the M genus of a knot K is the least genus among all the surfaces that the knot bounds. Now, there's some criteria of being smoothly and properly embedded, and so on and so forth. Don't really worry about that so much. Just think about it as what is the genus of the surface that the knot bounds, and in particular, what is the least genus. That is going to be denoted by G sub M of K. For instance, suppose we took a 4-manifold and we flattened the dimension. So this is like a cartoon of a 4-manifold, because obviously I can't draw 4 dimensions into a 2-dimensional plane and fully realize all those. We could do it with 3 dimensions using perspective drawing, but with 4 dimensions it's just utterly impossible in the traditional sense, though there are some cool ways to represent 4 manifolds actually by diagrams, fully capture the information of the manifold, which is really cool. We won't have time to get into that, unfortunately. But suppose I just kind of flatten this thing and we write everything in lower dimensions. So I draw a 4-dimensional manifold as if it's kind of a 2-dimensional thing. I draw a surface, which is usually 2-dimensional, and I draw it as a 1-dimensional thing and so on. So I've roughly halved the dimension of everything. Suppose this knot K in lavender bounds a surface that's genus 2. And then let's say you find in that same punctured manifold, you get a genus 1 surface, and then you get a genus 0 surface. Since 0 is the lowest we can get as far as the genus, we would say the M genus of K is equal to 0. So you're looking at all the different surfaces bounded by the knot that are in this manifold, M. The puncture just allows us to put the knot in the manifold. You look at all the surfaces bounded by the knot and you find what is the least genus that you can find among all of them. Now, just to make sure we're clear on what the dimensions are of the things we're looking at, we have a 1-dimensional object that is just the knot itself. Then we have a 2-dimensional object, which is the surface that's bounded by the knot. This is the Seifert surface that we've seen a few times. And then there is the manifold of 4 dimensions where that surface is embedded. Now, this is the essentially ambient manifold that we think of as surrounding the surface. So everything else is the 4-dimensional manifold, or at least that's how we'll think about it. For now, let's just focus on a particular 4-manifold called CP2, aka the complex projective plane. This C stands for complex numbers, P stands for projective, and 2 stands for plane, the complex projective plane. Now, one can describe this in a variety of ways. For our sake of time and scope, let's not worry about what it is exactly. We just need to know that it's a particular 4-dimensional manifold. What's particularly nice about it is it has a really cool property where you can determine if some knots are sliced using surgery and cobordisms. It's super neat. For CP2, there is this nice condition that we'll look at where we can say in particular that a knot is what's called slice in CP2. That means that its CP2 genus is equal to 0. That means in CP2 it bounds a disk, which is a genus 0 surface with 1 boundary component. And here's the condition. So if you have a set of n oriented band surgeries between a knot K and a standard oriented n link, if that set of surgeries turns K into the unknot, then we can say that K is slice in CP2. And now this probably sounds very complicated, or at least it's a lot of terminology to digest, but we'll look at an example that's actually relatively simple to resolve. You can find some slice knots in CP2 simply by drawing and manipulating diagrams in a fairly elementary way. It takes a little while to get used to, but at the end of the day, it's really diagram manipulation. And what you want to take away from this is essentially the following. Some surgery thing implies that K bounds a 2-dimensional disk in CP2. So what we're trying to do is find out which knots bound disks in CP2. Since disks are the simplest surfaces that a knot could bound. Some knots won't be able to bound disks, so maybe their CP2 genus is 1, but some of them will bound disks, and you can't get smaller than that because that's just genus 0. So let's check out how this actually works in practice. Say that you have a knot K like this. We said that you should be able to do oriented band surgeries on a n-link. Here, I've put a 2-link. Now, the orientations on each of these individual components could be different. They don't have to be like this. It happens that this set of orientations works out for this particular example. But you may try flipping one of the orientations, perhaps magenta, reverse its orientation, and that could allow you to do some different surgeries. But for here, we'll just use this 2-link. We claim that if you do oriented band surgery with, in this case, what will be 2 bands from a 2-link, And if we can get the result of that surgery to be an unknot, then we'll have shown that this knot bounds a disk in CP2. Now, that's a lot of sort of complicated ambiance, but the ultimate thing is we're doing some surgeries, and if we can get the unknot from it, that means this thing bounds a disk in a particular type of Bohr manifold, which is called CP2, the complex projective plane. Let's go ahead and do the surgeries. Now, they're band surgeries, which is exactly the type of surgery that we have seen so far. So the only surgery that we know or that you even have to worry about is a band surgery. The oriented part just means that you have to keep the arrows flowing in the right direction. For instance, let's go ahead and add in an oriented band. If we put an orientation on the knot, and then we put in a band, which can be thought of as solid, we see that the boundary components of the band align with the direction of this here. So if we follow this arrow around on the knot, we follow to here, here, so on, and around. Once we get up to this part, we follow back along the band, we follow along this magenta component, come back, and so on. Never do we have a case of arrows going against each other. Now what we do is we're going to substitute parts of this band with other parts. So we take the parts that connect to the magenta piece and to the knot, we remove those, and what we leave are these parts here. Now what we'll do is we'll manipulate this using some basic isotopy, thinking of these as sitting in three-dimensional space. We'll do some isotopy. Doing so brings us to this diagram where we've essentially reeled in the magenta part, and along with it has come the cyan component. Now we've done one surgery so far, one oriented band surgery. Let's do a second oriented band surgery. And now we'll do that from the cyan component to the knot. Again, we draw on the band. I've left out the center just for the sake of making this picture more clear. But then we'll remove parts of the cyan band and parts of the knot, like we've done here. Then we'll use isotopy to manipulate this a little bit. Namely, we'll pull this part and this part out from behind their respective bands to give us this. Now we'll continue to isotope. If we, let's say, move this portion of the knot downward, we get this. Now we'll pull this portion of the knot under this strand. Now pull this part to the left. Now take and untwist this part, and we get this. And hey, it's the unknot, which is awesome. So that means that the original knot we started with, which is here, that knot bounds a disk in CP2. And this is something you can do on your own simply by manipulating knot diagrams. In fact, you may be able to find out if some knots are slice beyond even those that I have found to be slice. So I hope you've enjoyed this video. Take care.
You